All right, here we go. Welcome everybody. How's it going? Max, the Ethernet is working great. I don't know if it's faster, but it feels faster. I haven't really been able to check or test that, but it's definitely working better than my previous garbage Ethernet cable was working. Um, that's crazy. Yeah, so hopefully I can teach you some chem, Jacob, along with all my AP kids. We're going to be talking about spontaneity of reaction. Hopefully we get some more people in here. We've got 22. Yeah, Caden, you can go away, but your brother should be watching this. He should be. So we'll give a couple of minutes for people to join in. I'll answer just kind of general questions. I do want to wait till more people get in before I answer specific questions, but any general questions about how this is working online? Comments about the earthquake this morning, which was crazy. I'm sure it woke up most of you, or anything along those lines. Um, Haley is Anna and Haley. Cool, good. Where's Sammy? Oh man, I'm tired. She's not allowed to leave her house. Well, that's okay as long as she's tuning in. I hope she's figured out how to do it at her house so she can join in the stream and we can talk about stuff. Um, oh, okay. So, Naya, I'll talk about that a little bit. The chapter 15 quest is on Canvas, and so the short answer portion, I want you guys to actually, write out on paper, and then you can take a picture of it and upload it. You can only submit a single file, so make sure that you either compile your pictures together into a single file, put them on a Google Doc or something, or just take one picture if you do the problem on one page, and then you'll have to upload it. So make sure your handwriting's nice and neat so I can actually see it and read it and grade your written work that way. Oh, but Sammy, you're here, so that's all that matters, right? Glad to see you here, even if you had to stay home. Um, okay, yeah, hopefully that makes sense, Naya. Hello, Isaac. So we have 31, which is if they're all AP kids, or at least we're getting close to having everybody for AP joining in. So we're missing a couple people. I made a couple of phone calls home yesterday to catch some people that haven't joined in yet. I'll be doing that again today to try to catch anyone that's slipping through the cracks because I want to make sure everyone has access. Scanning, if you have a scanner, Isabel, that would be fantastic. But a lot of people don't have scanners. So that would be the trick on that one. So make sure that you if like so iPhones have the ability to like scan a document, kind of they take a picture that turns it into a PDF. That would be fantastic. Just any way to upload it so it's nice, neat, and useful. Scanning would be great, but not everybody has a scanner. Okay. Um, yeah, my wife is super shook up because of the earthquake, because she grew up in California and they had a bunch of videos and things they had to watch about earthquakes, and so she's freaking out a little bit, but it is what it is, so nothing you can do about it. But a lot of people, Isaac, a lot of people are thinking that there might be a bigger one. There's always a possibility to have a bigger quake after a first quake. um, yeah, school during the earthquake would have been crazy. People would have been freaking out, but we're already home anyway. So yeah, there might be a bigger one. I don't think there'll be a big one, so who cares? Um, no, you're totally fine, Naya. Being gone yesterday is totally fine. You can go watch the stream on YouTube. You can go watch everything to stay caught up. Big picture ideas. We're just transitioning from Canvas. Lorderman Laws is Caden Smith. It's Parker's little brother. And then I get Stivix is Micah. So there we go. Caden, why are you watching this stream? You literally, it's not going to help you with anything. I don't want to ban you, but you might have to time you out for the whole class. Okay. Let's see. So let's talk about Canvas real quick. Most people, I think, have joined in. So with Canvas, real quick. So if you guys haven't checked out, there is now the AP Canvas is live and published, and you should be looking at it. This should be what it looks like on your end. So when you go into these things, right? So you'll see the introduction. This, of course, lists all the information that you need to see. It's got the stream times. Oh man, Canvas is struggling. Okay, so it's got the introduction. It's got, of course, the Discord link. You need to join the Discord if you haven't joined that. It's got the link to my Twitch channel, which you guys are all here, so you obviously have figured that out. And then a link to the YouTube channel. We'll all be uploading YouTube videos. So here's my daily schedule. This is what I'm going to stick to. So right now we're in this 10 to 11 time period. And I know, Naya, I had the exact same reaction when I saw that. Oh, the schools are closed. Well, duh, they've been closed. So anyways, I think a lot of people were having kids come pick up packets today. And so if you were going to pick up a packet, you can't do that today. You'd have to go pick it up tomorrow. They're forcing everybody out of the buildings. Yeah, Isaac, that's kind of the idea. All right, so like I said, here's all the stream stuff, here's all that stuff. So if you go back to the modules or the homepage and the modules page are the same. And so you'll see this quarantine to-do list. This introduction video was the stream from yesterday. Yeah, Canvas servers are super overloaded. They take so long to recognize that you've uploaded things. They are not ready to handle this, but that's okay. So if you haven't done the Chapter 15 take-home quest, make sure you do that. There's a way to submit your short answers as a file upload. We talked about that a little bit. Make sure you have to put that in there. The Chapter 16 reading quiz, again, when you get a chance, read Chapter 16, take the chapter reading quiz. It's open notes. I do everything open notes. Canvas it's doing okay. It's just kind of struggling a little bit as everyone is uploading massive amounts. Naya, that's up to you. It's whatever you're more prepared for. Technically, we should have had the quest on Monday. But then the reading quiz you can do is whatever you want. So I would probably do the quest first, and then you can jump into Chapter 16 and focus on Chapter 16. I also uploaded this morning, the AP Chapter 16 assignment sheet. So this is literally just the digital copy of what we would have seen in class. So what I would have handed out to you guys. So it looks just like everything. Oh shoot, full screen, yeah. So it looks like our typical assignment sheets. It's got the problems written out. So make sure after today you can actually do up to 19 if I get as far along in the notes as I want to. And so in terms of a due date, next week sometime. It depends on how far we get and how far we get through all this stuff. So, but the idea with the notes from today, you should be able to get up and done through problem 19. Okay. Yeah, it is a long assignment, Isaac. You're right. So anyways, if we post lectures, I'll be kind of just tacking on to this quarantine to-do list module. In case you miss any of the videos, there'll be links to them here that you can go and watch them. Of course, Naya, I'll still work through the assignments. I'll still work some of the problems. The class will run like it normally does. So today we'll do notes. I think that'll take the whole time today. But tomorrow I shouldn't have many more notes to do. We'll probably start and I'll work through a couple problems and I'll show you guys how to do all those. My hope and my goal is that we can function just like we would have if we were all in the same building. The other thing, if you look at the schedule, right, in the afternoon, I'll be available for help from 12 to 2. So I'll be in the Discord server. I'll be answering questions. I'll be looking at things, and I'll be doing all this stuff. So make sure that you, from noon to 2, if you have extra questions on the homework or you're working through problems, just hop into the Discord. I'll be there. I'll be able to answer questions there. And I'll do that. You can put your microphones on, and so we can talk to each other, and we can do all those things. So Monday to Friday, right? So typical, just a normal school week, just like we would have normally. I'm sticking to as much as I can, working, just trying to keep a sense of normalcy so that everything feels as normal as it can from home. Um, okay, Lauren. So if you're into the quest, let me just pull that up. So actually, go to modules. If you're in the quest, right, and you say take the quiz, blah blah blah. Okay, you got all these problems, multiple choice, multiple choice, multiple choice. So here we go. So you're supposed to just choose a file. So what you'll do on your computer or on your device or whatever you're using on your phone, you should be able to take a picture of something, take a like with your phone, take a picture, or if you can even type out your answers and type out and show your work. That's a little more work. Writing is and taking pictures easier. But you would find that picture, whatever that might be, upload it and then submit it. And then I'll grade those pictures this weekend. I think I'll have time. So yeah. So Lauren, hopefully that helps. Does that clear up the question on that? I'm not gonna give you the answers, Micah. Sorry. Yeah, you could. It shouldn't kick you out. You have one attempt. So as long as you don't submit it and then try to switch, as long as you are taking it on the computer and then logging onto the phone, it's fine. It should work. Okay, cool. Hopefully that helps everybody with that. Okay. All right, so that's Canvas. Let's go ahead and dive into the notes for chapter 16. No, we're not going to learn about magnetic flux through awkward shape. Sorry, Jacob. So chapter 16. Chapter 16 is all about spontaneity. Right? So we're going to talk about what makes a reaction spontaneous. So Isaac Lloyd Vitverel is Jacob Harris. He graduated 2 years ago. He's up at the U right now. He never took my AP class. He chickened out of my honors class too. But that's okay. I was intimidating. I'm still intimidating. Okay, so chapter 16, spontaneity. So Roman numeral 1. Right? So Roman numeral 1. Basically, what determines spontaneity? Now, again, I keep saying the word spontaneity. Spontaneity is just a fancy way to say whether or not a reaction is spontaneous. Now, when we're talking about reactions being spontaneous, we're not talking about, you and your friends that are like, oh, let's go get coffee at 4 o'clock this afternoon. It's so spontaneous. No, not like that. And that wasn't at Anna and Sammy and Haley, I promise. But the idea is that we're not talking about something that's just randomly spontaneous. It's more so that the reaction will proceed without some outside energy source, right? So the reaction will be able to sustain itself without some sort of outside energy source. Nice, Haley. Okay, so let's go with there are 2 factors that determine spontaneity. One we've already talked about, which is enthalpy. Okay. Reminder, enthalpy, right? That was our H. Okay. So this is going to be a little bit of review. If we remember enthalpy, we had a couple different ways to find enthalpy, but the biggest one we did was using heats of formation. So let's see. Enthalpy of a reaction using heats of formation. Right? So remember the delta H of the reaction is equal to the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. I ran out of room. Okay. Okay, so enthalpy of reaction using heats of formation, delta H of reaction equals the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So enthalpy, right? Enthalpy is just a fancy word for that really just means heat. So it's the heat content or the heat energy. And so when we look at delta H, that's the change in the heat or the change in the enthalpy, right? Remember we had a giant chart in chapter 8 that showed all these, it had a list of all the heats of formation. We talked about how an element in its standard state has a heat of formation of 0. All these things that we'll be coming back and we'll be reviewing and we'll be talking about. So remember that to find the enthalpy of a reaction, the delta H reaction, how much heat is either given off or produced, we can do it that way. Okay. So don't forget when we talk about the signs that a positive delta H means that the reaction is endothermic, and a negative delta H means that the reaction is exothermic. Right? Endothermic meaning heat has to go into the reaction. Exothermic means heat is given off by the reaction. So if your reaction requires energy, like some dissolving processes pull in energy in order they get colder as you do the dissolving. Exothermic, right? Things like combustion reactions, basically anything that gives off heat, we would say is exothermic. Okay, so in general, we could say in general, exothermic reactions are spontaneous. Now, that's not always true. That's why we say in general. But the more exothermic a reaction is, the more likely that it's going to be spontaneous. Okay, so the more energy that's given off, because if energy is given off, it's a downhill process, and so with it being a downhill process, it's more likely to occur and to drive the reaction. Okay, so in general, exothermic reactions are spontaneous. Okay, I'm going to flip the page, move on to B. Before I flip the page, any questions with any of this stuff right here? Self-sustaining is a good idea. Chain reaction, yeah, that's kind of a way to think about it as well. Just remember, like, if you have, a Bunsen burner, right? If you give it a spark just to start it, the flame will keep going. As long as you keep supplying methane, natural gas, it's going to keep going on and on and on and on. Another example of a spontaneous reaction would be, no problem. So non-spontaneous exothermic, that's a fun one, Naya. So at room temperature, right? At room temperature, water doesn't boil. Boiling is endothermic. Water doesn't freeze. Freezing is exothermic, right? So at room temperature, water is not going to freeze, right? Even though freezing gives off energy, it's not going to freeze. And so there are other factors that we're going to talk about. One of them being temperature, and one of them being our next one called entropy. So there are others but they all kind of, it depends on kind of the examples of these other factors that we're going to have to deal with. Okay, so let me make sure I answered all those questions. Yeah, more self-sustaining, chain reaction, let Sammy catch up with her fancy pens, and then I'm going to move on. Okay. So I'm not going to upload a file of the notes, Isaac, but I will post the video to YouTube. So you can go back and kind of just like click through the YouTube and catch the notes. I'll leave kind of the notes up for long enough that you should be able to catch the page with the notes on it, and anything that you miss, you can go back and write down. Okay, I'm going to move on to the next page. If you missed anything, go back on the stream later, go back to the YouTube later. Or, of course, yeah, you could pause the video. That would work too if you're behind. But you don't want to miss stuff because I'm going to move on. All right, so next idea, letter B. Yeah, we'll do it this way. Letter B. Do I want to write like that? Yeah, that's fine. Okay, letter B. Now, this is something new. We haven't talked about this. This is when if you've read the chapter and done the reading quiz, this would hopefully be what kind of stood out to you. So the idea is we have to talk about entropy. Right? Now, don't get enthalpy and entropy confused. Entropy is going to be represented by S. Okay? So when we say entropy, right, represented by an S, I don't know why it's represented by S. I don't know who thought that entropy should be S. Someone somewhere, yeah, capital S. But somebody did it, someone somewhere. Okay, so let's talk about what entropy is. So entropy is a measure of randomness or disorder. Okay. To kind of put it into, yeah, it's not a K, Austin. You're right. That's a really good thing that it's not another K. So when we talk about randomness or disorder, let's see if I can focus this. Randomness or disorder, we're talking about basically how many, the technical term is microstates. The book uses an analogy of dice and how a coin, if you flip a coin, it has two possibilities. It has heads and tails. But if you roll a dice, you have 6 possibilities. And so a singular die has 6 potential microstates, whereas a coin only has 2. And so we would say that a die has more entropy because it can be expressed more randomly. There's more randomness possibilities. Yeah, the RNG factor of chemistry. You're not actually wrong, Isabel. That's kind of a decent way to think about it. Okay, so if a reaction, so actually let's talk about the calculation first. So if we do a calculation, right, compounds, just like we had heats of formation, compounds also have standard entropies, right? So we have kind of entropies of formation as well. There's a chart in your book that shows all that. And so the idea is if we wanted to find the delta S of a reaction, it's the same as our heats of formation. It's the sum of the delta S of the products minus the sum of the delta S of the reactants. Right? So it's the same idea of, in order to find the change in entropy of a reaction, you take all the products, add them all up, multiply by the coefficients, minus all the reactants, add them up, multiply by their coefficients, and that tells you the change in entropy for a reaction. So if delta S is positive, that means more randomness or disorder. So it's going from an ordered state to a more disordered state. So you've got, say you've got like, a really solid crystal compound and it breaks apart and forms a gas, right? That would be a very positive delta S. If delta S is negative, right, it's becoming more ordered, right? And this can be confusing. You can get it backwards really easily, and so you have to be very careful that you remember that a positive delta S means that it's becoming more random, more disordered, and a negative delta S is becoming more ordered. Now, we'll get into these laws of thermodynamics probably tomorrow or yeah, probably tomorrow or Friday. But the idea is that the nature tends to favor more randomness or disorder. Things tend to go from an ordered state to a more disordered state. Everything is kind of, the universe is expanding, everything's spreading out, everything's becoming more and more disorder. So when we talk about disorder in terms of chemistry, we're talking about things like phase. So gas is the most disordered. Solid is most ordered. Right? So gas has the greatest entropy, and solid has the least entropy. So, Isaac, let me answer your question. Number 5. If delta S is positive, it's more spontaneous. So the most spontaneous combination between enthalpy and entropy is a reaction that gives off heat and becomes more random. So if you have something that's giving out energy and becoming more disordered, there's a very, very high likelihood that is going to be a spontaneous reaction. If you have something that gives off heat but becomes more ordered, it's kind of a give and take to which one is, the greater factor. Or if you have something that takes in energy but becomes more random, again, that could be spontaneous depending on, say, the temperature or something like that. So these are the two factors that we need to start to consider of if a reaction is going to be spontaneous. We have to think about entropy and enthalpy, delta S and delta H. Okay, so again, this is the new idea. I'm assuming you guys will have more questions about this. So not more unstable, Isaac. It's actually more stable if it has a positive delta S. It becomes more random is a greater stability. So in a reaction, if we go, so there's a couple ways to determine randomness, right? If you have a reaction that changes from solid to gas, that's becoming more random, right? Because you think a solid, the particles are really small and really tight and really ordered in the crystal, but in a gas, they're flying all over the place. And so in a gas, the molecules are much more free to move and to rotate, and there's more possibilities that they can be arranged, and so it's more random. But in a solid, you've got it more chunked together. There's not as many places they can move. They can't rotate. Do all those other things. Why is it more stable when it's more random? That is a hard question. So that goes back to just the way that the universe works. I wish I had a better answer. It's a probability idea. When something is allowed more flexibility, it's more stable, which I know isn't a great answer, but it has to go back to these microstates and this ability to express randomness. No. That means it's going to be, most likely it's going to be less reactive, Micah. So more random does mean more spread out. More random doesn't, it probably means it's going to end up being less reactive rather than more reactive. But the reactiveness is a little tricky. There's more to it than just that. But in general, we can think about it that way. Okay, cool. Everybody got this down before I jump on to our last factor. Is less random more Predictable? What do you mean by predictable? Um, yeah, Max, I'll give more real life examples. So, for example, if you have ice, right, and ice melts. So when ice melts, right, your water molecules are becoming more disordered, more random. Even though ice melting is an endothermic process, at room temperature, the ice can melt and turn into a liquid, and as it turns into a liquid, it becomes more random and more disordered, and it becomes, I guess, more stable when we're talking about room temperature. When it's more random, it's mean there's more opportunity for the right outcome. Not necessarily for the right outcome. It's just there's just more randomness, more states, more things. Yeah. So that's a great. The universe loves chaos. As things descend into more chaos, it's more stable. How is water more stable than ice? Well, if you put out a piece of ice at room temperature, it becomes liquid. It's more stable. But don't stress about the stability idea. We're going to worry more about the spontaneity and where the reactions are tending to go towards. And let's see. I'm imagining less random solutions, chunky stuff, and randomness is spread out doing whatever I want. Yeah, that's fine. Yeah, that works. Yes, Isaac. Yeah, no, you're right, Isaac, on that. Or Micah, sorry. That less random solutions is chunky stuff and randomness is spread out. Yeah, phases for me is the easiest thing to grasp onto. To think about, as we go solid, liquid, gas, we become more and more random. You can also think about small molecules versus, a big chunky fat molecule. So something like DNA has a very low entropy because it's a very large, very ordered molecule. But something like, I don't know, individual molecules of some sorts, like man, I don't know. Yeah, Max. So that gets into the laws of thermodynamics and about how the universe is constantly expanding. Yeah. That's in the text. So if you haven't read chapter 16 yet, you'll read and find about that towards the end of chapter 16 when it talks about the laws of thermodynamics, which we're not going to talk about today. We'll get into tomorrow and the next day. Okay, so I'm going to move on from entropy. I'm going to talk about our last factor. Oh, predicting state of matter. Yeah. The idea that more space, more spread out, is more entropically favored. It's more favored in terms of entropy. Okay, cool. Last thing, letter C, is temperature. Right? So temperature is our last factor that affects whether or not a reaction will be spontaneous. So we take into account the change in entropy, delta S, the change in enthalpy, delta H, and then also the temperature. Now, depending on how much the other things, what the values of delta H and delta S are, sometimes we might want a high temperature and sometimes we might want a low temperature. Temperature, so spontaneity. Oops, man, I can't spell. There is an equation, Isaac. There is an equation that we're getting to. Yeah, we can get to that today. I think, yeah. I'm going to write that down next. So, let me make sure that I'm right on the notes here. Sorry. Yeah. Okay. So let's actually go into that last factor. So this is letter D. This is called Gibbs free energy. Delta G. Okay, so Gibbs free energy is going to be our measure of spontaneity, right? So it's going to be how do we determine, how do we predict is a reaction is going to be. I don't think it sounds as cool as P equals nRT. Nothing sounds as cool as P equals nRT. So what the equation is delta G equals delta H minus T delta S. Okay, so delta G equals delta H minus T delta S. This is the equation. This is our equation for Gibbs free energy. Now the sign of delta G, if delta G is negative, the reaction will be spontaneous. If delta G is positive, the reaction will be non-spontaneous. Okay, and yes, indeed. Temperature, like always, temperature must be in Kelvin. So just like with our gas laws, temperature must be in Kelvin. Yeah, it's T. This is a multiplied. So, right. So it's T multiplied by delta S. Temperature does have to be in Kelvin, Maggie. Good call. Yeah. Okay. I don't want to dive too much into this equation today. I want to save and talk about it tomorrow. What I want to do today is I want to do kind of for the last 10 minutes or so, I want to do a calculation. So I want to show how would we calculate. Okay. So they're all going to be in joules. So it's going to be energy. Let me use an example problem to illustrate that, Sarah. That's a great question. So let me make sure everybody gets this down, and then I'm going to go to a new page and do an example problem. Yeah, watching a small child is tricky, Isabel. You're right. I'll try not to go too fast. So Gibbs free energy, right? Named after Gibb. I don't think he called it Gibbs free energy. I think he just called it free energy. And after he died, they decided to name it after him. Naming things after people is always weird. So if we look on this, right? If we think about the combination of signs that we could get, if we want delta G to be negative. Gibbs is really important. If we wanted delta G to be negative, right, if we think about the signs, we want delta H to be negative, and we want delta S to be positive. Because if this is negative and this is positive, no matter what the temperature is, we'll always get a negative value here, and so the reaction will always be spontaneous. And so an exothermic reaction that becomes more disordered will always be spontaneous. Naya, great question. How do entropy values get calculated? From your textbook. There's a giant table that we'll be using, just like delta H values. All right, so I'm going to move on. I'm going to do an example problem. Okay, so let's go. This is letter E. We're just going to call this example calculations. Okay, number one. Calculate delta H, delta S, and delta G at 25 degrees C for the following reaction. Okay, let's do Fe2O3 solid plus H2 gas makes, 3 H2 gas makes 2 Fe solid and 3H2O gas. Okay, so before we get into the calculations, let's just look at this reaction and see if we can predict a few things. So we have iron oxide solid plus 3 hydrogen gas, making 2 iron solid and 3 water gas. So if we're predicting, okay, is this reaction going to be endo or exothermic? If we think about endo and exothermic, we've got 4 molecules on the left and we have 5 molecules on the right. And so because it's breaking down, you would most likely predict that it's going to be endothermic because we're breaking bonds, right? Remember, breaking bonds, endothermic, you have to put energy in. Forming bonds, exothermic, you get energy back out. So as we go from 4 compounds to 5, I'm predicting, I don't actually know, I'm predicting it's going to be exothermic. In terms of entropy or randomness, or sorry, endothermic. In terms of entropy or randomness or disorder, again, we're going from 4 molecules to 5. And the number of gases is staying the same, right? If one side had more gases, we would predict that side to be more random or more disordered. But we are breaking this compound down into 2 smaller compounds. So maybe it's going to become more random, but that's a tricky question. We'll just have to kind of see what the numbers come out to be. So, hi DJ, I'm glad you were able to get your chat working. So let's dive into how would we actually solve this problem. So the way we're going to solve this problem is we're going to pull out our textbooks. So let's first find delta H, because that'll be a review. To find delta H, you can either use the chart in chapter 8, where are you, chart in chapter 8? You are right here. So you can either use the chart in chapter 8 on page 203 that has all the heats of formation, right? You left your book at, you are home, Micah. You're at home. Okay, anyway, so you have all of the delta H values, okay? Or, so you can either use this table for delta H's, or if you look in the back of your book, oh, here it is. On page 601, there is a larger table, and this table includes delta H values, delta S values, and then delta G's at 25. So they've kind of thrown this equation at you anyway. So this chart also shows all the delta H, all the S values, and all the delta G values. So yeah, and then in, let's see, in the chapter itself, let's see, I think there's a table in the chapter. Oh yeah, here's the table in the chapter. So if we want our entropy values, okay, it's also up on page 411. So those pages were 203, 411, and 601. So delta H, oh sorry, delta H 203, S 411, and then delta H, S, delta G 601. Okay, so you have all these tables on all these pages that you can use. Okay, so let's use the table and let's look up all the delta HF values and the S values. So if we look at the chart, make sure you include the state. So if I'm looking on page 203, right, looking on page 203, okay, I'm looking for iron oxide, Fe2O3, it's right here. So iron oxide says negative 824.2. So negative 820, oops, gosh dang it, 824.2 kilojoules per mole. Okay, so iron oxide is negative 824.2. Hydrogen's not in the chart. Why isn't hydrogen in the chart for delta H's? It's an element in its standard state. It's 0. Yay! You guys remembered something. Okay, so it is 0 because it's an element in its standard state. Remember, the heat of formation for an element in its standard state is always 0. You guys are smart. Okay, so iron solid, of course, will also be 0 because it's an element in its standard state. Water, make sure you grab water as a gas, not water as a liquid. They have two different values. So make sure you watch the phase on these. So water as a gas is negative 241.8. Again, kilojoules per mole. All right. So, yeah, it says kilojoules per mole. Sorry. Kilojoules per mole. Kilojoules per mole. So if we look on, now if we transfer over to page 411, right? On 411, okay, we have our entropy values. But notice the entropy values are in joules per mole Kelvin. And that has to do with this temperature factor. So joules per mole Kelvin. Notice joules, not kilojoules. Joules per mole Kelvin. So if we look up iron oxide in this table, where are you, iron oxide? Iron oxide, Fe2O3 is 87.4. So 87.4 joules per mole Kelvin, right? 87.44 joules per mole Kelvin. Now, hydrogen, being an element in its standard state, will not have an entropy value of 0. So we do have to look up the entropy value for hydrogen gas. So hydrogen gas's entropy is 130.6. So 130.6 joules per mole Kelvin. Real quick, why is hydrogen's entropy value greater than iron oxide's entropy value? It's a gas, right? Gas is more random, more disordered, more ability, more microstates, right? So this is much more disordered than this one is. That's why it has a much greater S value than iron oxide does, okay? So iron solid, right? That's probably going to be a pretty small value. Iron solid is 27.3, right? 27.3 joules per mole Kelvin. And lastly, water as a gas, we would expect to be a pretty high value. Again, it's a gas. Water as a gas is 188.7. Right, joules per mole Kelvin. Okay. Bigger molecule can flop around. It's got more potential ways to orient itself, which means it has more disorder, more randomness. So our most disordered molecule is water as a gas, right? Then hydrogen as a gas. This iron oxide compound's big, and so it has more. Yeah, all the S values are going to be in joules per mole Kelvin. When we plug them into the formula to find delta G, we'll have kind of an issue that we'll talk about when we get there, right? So for now, though, let's... yeah, so the chart pages, right? 203, 411, 601. Oh, so remember, elements, iron solid, hydrogen gas, elements in their standard state have enthalpy values of 0. That's just kind of how we defined delta H of formation. An element in its standard state will always have an enthalpy formation value of 0. Okay, hopefully that answers your question, Lauren. I'm not going to post the chart pages. You guys should all have your books. Go get your books. Use your books. You can also just look them up online. There's online tables everywhere. Isaac said he might post one that people can use. But yeah. Oh yeah, so Isaac already posted one in the Discord. So if you guys look in the Discord, in the Discord, Isaac already posted a thermodynamic chart, which is downloading. It's a PDF. Look at that. So there you go, Naya. There's one you can use. Steven, this is AP. You're in honors. Okay, so it is in kilojoules per Kelvin mole on 601, and the reason why is because of a conversion that we'll have to do. Yeah, Stephen, honors is from 8:30 to 9:30. You can check the video on YouTube. It's up and posted. All right, so let's actually now put my books down. Let's do the calculation. Shoot, I'm running a little late. Let's see if we can do this calculation real quick. So the delta H of reaction is going to be the sum of the products. Okay, so 2 times 0. Don't forget we have to multiply by the coefficients. Plus 3 times negative 241.8 minus the sum of the reactants, negative 824.2 plus 3 times 0. Okay, so that's going to be our delta H of reaction. The delta S of reaction, we're going to do the same way, except it's going to be 2 times 27.3 plus 3 times 188.7 minus 87.4 plus 3 times 130.6. Okay, I did that really fast. So I wanted to write it down just to kind of show you guys what's going on here. So the idea is that we always take the products minus the reactants and we multiply by their coefficients. So for the delta H, we took 2 times the delta H of iron, which is 0, plus 3 times the water, right, because of the coefficient of 3, minus the 824 from the iron, plus the 3 times 0. Who is texting me? Okay. Sorry. All right, so then our delta S, 2 times this plus 3 times that, okay, minus 1 times this plus 3 times that. Okay. So we should be able to figure out our deltas, our delta H and our delta S for the reaction. So let me grab my calculator. Uh, 3 times negative 241.8 plus, actually not plus, minus 824.2 negative, minus a negative. So I get a total of positive 98.8. And again, that's kilojoules per mole. Okay, so because this value is positive, that tells us that the reaction is endothermic, kind of like we predicted. We predicted we would be breaking bonds, and so it's probably going to be endothermic. Now for our delta S value, 2 times 27.3 plus 3 times 188.7 minus 87.4 minus 3 times 130.6. So I get 141.5. And again, that's joules per mole Kelvin. So make sure you guys check, see if you got the same things for delta H. I mean, I'm using my crappy phone calculator, so I might have messed up somewhere. Double check, make sure we get the same values for delta H and delta S. That should be right? That's like negative 750. Yeah, that should be fine. That's, what is that, like 600 minus, yeah. Okay, good. Thanks, Sarah. So we now have our values for delta H and our value for delta S. Again, the sign of these values tells us that it is endothermic, right? And then the sign of this tells us that it's becoming more disordered. So it's endothermic and it's becoming more disordered. So in terms of calculating delta G, let's go ahead and do that. Because I ran out of room on the other one. I'm sorry if it triggers you, Sammy. Okay, so let's take these values and let's plug them into our delta G equation. Delta G equals delta H minus T delta S. We said we were at 25 degrees C, so remember 25 degrees C, that's 298 Kelvin. Okay, yes, I could have put this one underneath, you're right. Deal with it. Okay. All right, so delta G equals delta H minus T delta S. 25 degrees C is 298 Kelvin. So now we have to plug in. Now you have to be careful because this value is in joules and this value is in kilojoules. We might have to just change this into kilojoules. So changing to kilojoules is a quick just dividing by 1,000. So we're going to move that decimal over 1. So delta G is going to equal 98.8 kilojoules per mole minus my temperature, 298 Kelvin, times my delta S, but I'm going to change it into kilojoules. So 0.1415 kilojoules per mole Kelvin. Okay, so we've got our 98.8 kilojoules per mole, or delta H. We have our 298 Kelvin for our temperature, and then we have our delta S, which we've converted into kilojoules by dividing by 1,000. So now if we evaluate this, this should tell us the delta G for the reaction. You're right, Sammy, it wouldn't be. So 98.8 minus 298 times 0.1415. So we get 56.6. Right, so a positive 56.6 kilojoules per mole. So what does that mean about this reaction at room temperature? What does that tell us? Because this is positive, it means it's non-spontaneous. Yeah, good job, DJ. Non-spontaneous. Okay, so if it's non-spontaneous at this temperature, that doesn't mean it's non-spontaneous at all temperatures, right? If this value was bigger, right? So if it was like 1,000, then this minus term might be large enough to turn delta G negative, which would make the reaction spontaneous. We'll get into all the nuances of all those calculations tomorrow. No, so activation energy is a different thing. Activation energy we'll talk about later. Even spontaneous reactions might require some sort of activation energy. But the idea is that for a spontaneous reaction, once you get that activation energy, it's going to continue to react until things are used up. Our page numbers, right, for our delta H, S, and delta H, S, and delta G were on page 203, 411, and 601. Okay, I went a little late, but I wanted to get through this last one. Yeah, Sarah, it could potentially. Whenever we do these calculations, we're assuming that the temperature is constant, but in all actuality, the temperature is constantly changing, and so you would have to monitor that temperature and adjust in order to get, whatever calculations you want. But again, that's real world that gets complicated. Changing joules to kilojoules is dividing by 1,000, right? 1,000 joules is 1 kilojoule. So if it's non-spontaneous, it will be an equilibrium reaction. Not necessarily. Non-spontaneous, we'll talk about kind of what that means in terms of the reactions more tomorrow. Non-spontaneous would be that instead of the forward reaction being favored, the reverse reaction would be favored. So instead of the reaction going in a forward direction, it would go in a reverse direction. But we'll talk more about that later and tomorrow. So the big thing for now, just make sure you understand what entropy is, kind of what it means, what it's measuring, and then kind of how to use this delta G equation. And if you got that, you can really dive into the homework. Cool. Okay, it is 11. I don't want to go past 11. Any last and final questions? Gillespie, wait up. Okay, any last and final questions? So the homework is going to be due sometimes next week, Rhett. We kind of, because we're not having class every day, we can go there. What does it mean by... Oh, that's the page number. That's the page number. Sorry, Isaac. That's page. Page 601. That's the chart that has all three. That's not the values, that's the page. Yeah. Sorry, I can see how that would be really confusing. My fault. The test will potentially be on Canvas next week, most likely. This is pretty much a homeschool stream, chmod boom. Okay. But it's because we're quarantined. Any extra credit on the quest? Probably. I'm still working on through all that. It depends on how everybody does, and who knows. So, cool. Okay, so the homework, right, is going to be sometime next week. So I would dive into it tonight so you can ask any questions. Of course, there'll be extra credit. We'll worry about all that later. But I do want to go ahead and close out, because I know you guys have extra stuff you want to do from your other classes, and I don't want to take more of your time than I've already taken. Cool. I'll go ahead and end the stream, and I will post this up on YouTube. What question can we get to? That's a real good question. If I'm not mistaken, you can go all the way up to 37. So like a really good chunk of it. I would make sure to finish the reading quiz if you haven't done the reading quiz yet, and then I would get through at least the first couple of problems. The first couple are conceptual, and so you should be able to get through those. Cool. Okay. I will set up the YouTube video. I'll send that out. I'll post the links to Canvas, and you guys have a great day. See you back tomorrow, same time, same place. Sounds great. Good night. It's 11 in the morning. Okay. Have a good day, guys. See ya. I'll be in the Discord this afternoon from 12 to 2, and you guys can ask questions if you start working on the homework then. And here we go.